And we also found out by equilibrium, enforcing equilibrium, that these two, tau yx and tau xy, are one and the same, right? If tau xy and tau yx are one and the same, and if I write it in this kind of matrix form, okay, I'm just going to say sigma at P. Okay, so I'll use this. Sigma at P is equal to, okay. This is the rows are pertaining to phase, the columns are pertaining to the direction of the force. Okay. What all do we observe here? Number one, because we found these two to be the same, this matrix is quickly. This matrix is, folks, we're not responding today that much. Symmetric, correct. Okay. All right. And how many quantities that we have here, which are distinct? There are three quantities that are distinct. Okay. Three quantities: sigma x, sigma y, and tau xy. Okay. Sometimes we will be writing this to be just sigma x. Okay. And there is a repetition like this. So this is also something that we may start to do in case it becomes simpler to write. All right. Just want to get a feel for how it would be in the 3 dimensions. Okay. Let's just write one on this, and that's it. Okay. So point P is inside. Okay. Then one we have here. Okay. So let's say this is X, Y, and Z. Okay. Let's look at this first and draw all the stresses that are possible here. XX, I can write the sigma X, all right? The only normal stress, okay? So what is this and what is sigma Y? Normal stress. The other component would be in the Y direction. Go ahead.
Tau xy.
Tau xy. And we'll have the third one available now, which would
Tau
be
xz.
tau xz. Okay. Let's look at the Y direction now. All right. So here it will be sigma Y.
Y
Tau
x.
xy. Xy is fine.
Okay.
All right. Why? Because it's symmetric. Correct. I'm just drawing induction from here for the 3 dimensions. Here in this would be tau. We used xz here. We'll use the similar here yz. Okay. And we will have 3 over here. Quickly, this is sigma z, tau yz, and this is the same as this. All right. So 3 plus 3 plus 3. Of course, on the other sides, the conjugate sides have not drawn, but you are supposed to draw there also. I have 3 of them over here. So in which case, the matrix will be a little larger. It will be X, Y, and Z also. Right? That's all. So here it would be tau xz. Here it will be tau yz, tau xz, tau yz, and sigma z. Similar to the previous one, this is also symmetric, right? So since it is symmetric, we only have the lower or upper triangle that we have to bother about. There is 6 quantities. Okay. I'm just doing all this for completeness. Let's say I have a vector. I have a vector, okay? Let's say this vector is V. Okay, when I put a wiggle here, it means a vector, okay? Let's say I have a coordinate system, X and Y. And just two dimensions I'm looking at. Now, what are these X and Y as far as this vector is concerned? What are these X and Y? So this X and Y is a reference, all right? I'm just trying to share how I understand it. Supposing I change it, I don't like this X and Y. I only like X prime and Y prime. Is my liking okay first? Is my liking okay? You will respect my liking? All right, okay. Now, what's the difference between this X and X prime? What's the difference? What's the difference between these two? Quickly. As you respond, it becomes easier for me to share my understanding. Different orientation, different angular displacement. One thing is clear, which you have not mentioned over here, it is different. It is different from X. Okay. Perhaps the person is sleeping and watching the person upside down. Right? So it is about another reference frame or reference coordinate through which you are seeing this V. Okay. Now, how do I describe V from the angle of X and from the angle of X prime? All right. How do you do that? How do you do that? I'll repeat it again. When I'm looking at somebody who is upside down, the person who is actually lying, who is another reference, is seeing the other person just tilted 90 degrees. To describe the same vector, how do I describe with respect to each one of them becomes a question, correct? And therefore, what I would do is something that you already know. You would use the projection of this, the projection of the vector onto whatever basis, somebody said basis, whatever basis that you chose for your coordinate system. So this would be Vx, Vy. The same vector, nothing different. This is with respect to X and Y. So I'm going to now call this as with respect to X and Y. Okay. The same guy, the same vector, but with respect to X prime, Y prime would now be different. Is this clear to you? This is something that you've done earlier. I'm just bringing it back. So there is a vector here which can be described differently by different orientations. Somebody said orientations or angular displacement of the basis by which I want to look at this vector V. All right. But what do I know very clearly? This vector is unchanged. It is only the references that are changing. Right? Supposing I choose something that is along the vector V like this, I know the perpendicular y double prime here, the component along double y prime would be 0, right? Because I'm looking at projections, right? How x sees this V, how y sees this V, how x prime sees this V, y prime sees this V, x double prime sees this V, y double prime sees this V. All right. And therefore, one thing that I understand, and I'm going to write it very clearly, is the vector as a quantity or a measure does not change, it is only the reference that changes. Another thing that I know about this vector V is this vector is a magnitude, a Euclidean magnitude, plus, this is how I describe vector, a magnitude plus a single direction. A single direction attached to it, correct? That's how I describe vector. And using that, I'm able to describe or define this vector using any of these references. Even if there are no references, this vector would exist. Okay. Okay. With this idea, I'm going to just move on to what we now looked at, which is sigma. Okay. So we wrote this matrix sigma xx, tau xy, tau xy, sigma yy, right? How did I see this stress? Definitely through the eyes of x and y, is it not? Okay. So I saw some quantity sigma at a point P with respect to a reference that I chose, which is x and y, right? Or in other words, what I'm saying is I have chosen this box. Who asked you to choose the box? I decided to choose the box, which means that if I want to change the box, it is left to me. Clear? And therefore, let's change it. So same point P. This is on the body that I picked up. Okay. And then sectioned it in those directions of x and y. This is what I did. Okay. But I don't like this. I prefer something else. So I will go for something like this. Can I? So one is like this. The other is like this. The same point P. Can I choose like that? I want to describe the stress of the point P, by choosing two boxes. I will let, so this is dx, this is dy. I will let this dx prime and dy prime to be the same. Dx and dy tend to 0. I will also say the x prime and dy prime also go to 0. What's wrong? Both of them will give me the same P at the end, correct? Which means that I can take this or this. What is unchanged is this description of stress. If this is clear to us, then it becomes easy. There is one difference between this vector that I chose and this quantity that I've chosen. I'm going to now introduce a wiggle, since now it becomes clear that that remains as such, and the way in which the lens with which I'm seeing it is different. I'm going to call this as an independent. Can I say vector? No, vector means there is only one direction, but this guy has phase, which is x and y, and the direction of the force x and y, which means I have two directions right now. Okay, one direction that is attributed to the phase on which I'm looking at the quantity. The other is the direction in which I'm looking at the quantity. But one golden thing that I have found out is, while this may have some magnitudes, we'll come to what would be the magnitude. What would be the magnitude of that? Some of you would have done linear algebra know it well, but just listen to me. One is, as far as the simple vector is concerned, you have a magnitude and a single direction. One thing that we have figured out is it is not a single direction as far as this stress is concerned. It has two directions. So one thing I know is two directions. One for the phase and one for the force. Okay. So this is a vector. So this is a vector. And this, I need to name it. I'll come to that in a minute. How about the magnitude? Magnitude is not so simple to immediately tell you, but it will have magnitudes. What's the difference between magnitude and the direction? The magnitude as such remains unchanged, Not that direction is also not changed. Remember, the direction as such depends on how I am viewing it, upside down or erect, right? But as far as magnitude is concerned, it's the same tall person that I'm seeing from one to the other. And therefore, magnitude cannot change, correct? Which means that whether I'm looking at from this eye or this eye, what does not change are the magnitudes. I don't know whether it is one magnitude, so I'm going to add an S to it. Magnitudes, okay? We'll figure out whether it is a magnitude or magnitudes, but definitely two directions, okay? These directions, depending on the reference, I will say it is upside down or erect or lying down, etc., etc. Is this clear to you? Given this, let's go back to what we did earlier. Shall I erase this? Any questions on this? Is this clear to you? This is an important principle. Once we understand this, it's easy for us to make sense out of whatever we are going to do later. This is termed a tensor. Okay. I'll come to it. Any questions on this? Whatever we discussed so far. Okay. There are many quantities. For example, force is a quantity which is a vector. Displacement is a quantity that's a vector, right? Similarly, we may have more such ones which have two directions and the magnitudes associated with them. Okay, we will have even a different tensor that comes into picture. I will explain to you later when it comes to that particular when we discuss about that concept. I'll erase it now and ask this question that we had earlier. Before moving on, I said tensor, right? Tensor is a very common word. Common word used in linear algebra. Okay, a tensor is also called something that linearly transforms one quantity into another quantity, just like what we saw here. If I have in terms of xy and in terms of x prime y prime, I have two quantities, and this is a linear transformation that we are looking at. But it's not a fancy name for matrix. Matrix is a sort of more crude form of a tensor, okay? Because tensor has this linear transformation attached to it. Okay. Hey folks, mute. Yeah, okay. All right. This is a common word. So I attach with this tensor of order 0, 1, 2, and so on. Okay. Vector is a tensor of order 1. What is a vector, a tensor of order 0? What is a tensor of order 0?
A scalar.
It's a scalar. Fantastic. Okay. Okay. And this is a second order tensor. After that, see, once you name the first and second child, the third child is third child, fourth child, fifth child, like that. Okay. So the third one is third order tensor. Fourth one is fourth order tensor, and so on. Okay. We may go up to fourth order tensor when we discuss concepts in strength of materials. So far, so good. Any questions? All right. All right. In a previous class, we did something where we had stuck in an oblique direction. We had sigma over here, and then asked the question, what would be these stresses? Sigma nn and sigma nn prime, this direction being n prime, which is perpendicular to this direction, which is n, which is at an angle theta over here. Okay, we did this exercise and we got something like, one of you can help me out. Sigma nn was equal to, you remember? Sigma by 2
cos 2
plus
theta plus
1
sigma by 2
cos
cos
2.
2 theta.
cos 2 theta.
Right? I'm explicitly writing it like this so that I can explain to you better. Sigma nn prime came out to be sigma minus sigma by 2 sine 2 theta. Yeah. I can also write this as minus here and then take it out. Minus this is equal to. Okay. I'm going to call this as sigma bar nn. Just to get a meaning to it. So I have this. The amplitude is the same. This is cos 2 theta, sine 2 theta. What do you understand from this?
Sir,
One
locus of circle.
Locus of a circle. Fantastic. And what else can you gather if you draw a graph with one as theta and the other as the quantity? What did you find? You draw these two with x-axis as theta and y-axis as sigma nn or sigma bar nn or sigma nn prime. What will you get? What kind of curve will you get? I know it's a mundane question I'm asking. Periodic. One other simpler repetitive. There's a simple word to it here. You forgot. What form of the curve will you get? Waveform. Waveform. Right? It's a waveform. But what do you understand by these two terms? These two, when I draw in the same graph, what will I have? I'm drawing this and this in the same graph. What will I see? Shifted curves. Shifted curves. What's the other name for shifted curves? It starts with PH. Phase. Those with a phase difference. Whenever you have something of this sort with a phase difference, they actually are in the circular coordinate system, not polar, circular coordinate system. Okay, phasor, fantastic. Kishore seems to know it, right? And therefore now I can draw it very nicely. First, let me draw sigma nn bar and sigma nn prime. Okay, you got to help me out. Each one that you come up with, I want to draw sigma nn prime versus sigma n versus sigma n. Remember, this is sigma bar nn versus sigma nn prime. Go ahead, tell me. Let's say I start with 0 from here. Okay. Quickly. I know here it is when it is along the x direction. Let's say this is the x direction. I only have pure in the x direction, I have only pure, yeah. What is that sigma by 2? It is pure
So normal.
normal. So this is a normal stress. This is a shear stress. I'm going to now change it. Okay. I'll just say this. Uh, okay. Normal stress. Okay. I'll say shifted normal stress. Why I'm saying shifted is I have a sigma by 2 that is subtracted. And this, how about sigma nn prime? What is that? From the physical understanding?
Shear stress.
Shear stress. So this is the shear stress. In other words, this is sigma. Okay. When I say sigma, it is normal stress. Here it is tau, which is the shear stress. Just to distinguish between the two, whenever I write sigma, it is the normal stress. Don't confuse with the tensor that we are only looking at one value over here. Okay, sigma versus tau. We are going to draw this, and a couple of you identified that it is in a phasor or a circular circular notion, right? Help me out identifying points for this quickly. Number one, use this fact. Quickly. 0, 0, sigma by 2, fantastic. 0, sigma by 2 is one of them. The other is 0 minus sigma by 2. Is it 0 sigma? 0 sigma by 2 is here? No? Sigma by 2, 0. Minus sigma by 2, 0. Okay. Sigma by 2, 0. Actually, here it is minus. So I'm going to just shift this to this direction like this. Okay. So this is a minus. I'll tell you why I'm doing this. Minus sigma by 2. I'm sorry. 0 comma minus sigma by 2. And this is 0 comma sigma by 2. Okay, about 4 points are there. I know it is circular, so I can just indicate these points and say, okay, this is circular. And what is it that I'm looking at? Any point on this denotes the cutting that I did, right? This angle that we are representing. What is the angle that it makes? Supposing I take this point, what is the angle it makes? It is not theta, it is 2 theta. So far, okay? Is this clear to you? Yeah. Now, how do I get the center? I can add the value of this point and this point in the x direction, and that will give me the center, right? And the center does not change for any of these points when I evaluate. I'm going to just take 2 more minutes to explain this very clearly. What do these points indicate? Each of these points, this is, let's say this is x, y, this is x prime, y prime, and so on. This is x triple prime, y triple prime, and so on, x4, y4, depending on the inclination that I have taken in order to section this. Correct? Is that clear? So that I form a circle. When I come back to pi by 2, which is 180 degrees, I get the same quantities back again. Okay? As simple as this. Of course, I have a sigma NN minus sigma by 2, which means I have to now shift this curve, right? How do I shift this curve? That's very simple. All I have to do is just shift it by sigma by 2. Okay, I'm sorry. So it will actually pass through the tangent of this, right? This is the actual tau axis, and this is the actual. I'm going to remove the shifted normal stress. It is now possible for me to represent any of those quantities which pertain to the oblique cutting that I have made here. Clear? Any questions? Any questions? Is the concept clear? This is popularly called, due to Morse circle. Because in those days, during Morse time, which is 2 centuries, 1.5 centuries ago, during Morse time, it was easier for them to plot and obtain the values. Supposing I have to obtain the value here, anywhere, it is possible for me to draw this circle and measure what would be the values. It's easier that way because a calculator was a non-existent quantity object at that time. Okay. Okay, folks. I know it is afternoon. Some of you have had lunch and it's heavy. So, sir, why is 0 sigma by 2? 0 sigma by 2 is the shear, right? We got this from here. Is it not? 2 theta. 2 theta. When 2 theta becomes pi by 2, then this becomes 1 minus sigma by 2 is what I have drawn here. Remember, the axis that I have drawn here is downward now. And therefore, this is minus, this is plus. Okay, that's the only difference. The reason why I changed it like this is I want to use an anti-clockwise rotation over here. That's all. That's all. If I did it clockwise, then this would have gone up. Okay. But that complicates the issue. So I have just changed it to downward direction for tau.